actually exist in many areas of scientific research. Today I want to talk about multiplicity issues for small samples. So when you have a trial where you don't have a big sample size, this is where there has been less focus in the literature and in practice, and also some interesting conclusion we can make out of this is potentially you can get multiplicity issues solved for free, or multiplicity is beneficial in this scenario. So let's see how it works. So the title is Optimal Test, Exact Test for Multiple Binary Endpoints. So we're looking at binary endpoints with small samples. So we choose to use the exact test instead of the asymptotic tests. This is a joint work with my colleague Eka Flynn and also two collaborators, Robbie Bristol and Martin Hosch from Medical University of Vienna. So some backgrounds. In clinical trials, usually large sample sizes are really needed to really confirm the efficacy of the treatment. However, in practice, large sample sizes may not be feasible in some situations. For example, in pediatric trials, it's usually very difficult to recruit patients. In rare diseases where the population itself is very small, or subgroups, if you have a large sample, if you have a large trial, but you have 125 subgroups, you can imagine for each subgroup, you have a very small sample size. So here our focus is on confirmatory clinical trials with small sample sizes. You can think of example as a phase 3 trial for a rare disease. So in this case, although you're dealing with a small trial, but multiplicity issues could still exist if you want to look into multiple aspects of the investigation of the treatment. So the impact of small sample sizes, right? So because many of the statistical tests, they are built on asymptotic distributions, normal distribution, chi-square. So we know that when the sample size is not large enough, the approximation is not accurate enough. And also, for these distributions, really you have some nuisance parameters to estimate. With small samples, it will be even harder to give a precise estimation. And also, for these small sample sizes, you may want to introduce some modeling technique to help you to better identify the treatment effect. But with such a small sample sizes, you're risking yourself about overfitting, and also you couldn't fit some of the complex models in the data sets. And probably one of the direct impact is the low power, because you just don't have enough, you couldn't have enough sample to ensure like 80 or 90% power. So here, we want to use the exact test, which whose distribution of null hypothesis is exactly known. Okay, so under the alternative, it may be more complex, but under the null hypothesis, usually you can know the distribution exactly. This is often achieved by using sufficient statistics or conditioning on statistics, sufficient statistics or permutation tests. The benefit, obviously, is to alleviate the problem of inaccurate asymptotic approximations, and we don't have to worry too much about the nuisance parameter. And the drawback, is usually these tests are discrete. So when you have discrete distributions, usually it will become very conservative, and we will see how conservative it can be. Probably this is one of the most popular exact tests, right? Fisher's exact test too. This is comparing a treatment versus control, and you're looking at the number of successes and failures in the two groups. Usually, you will have this kind of 2x2 table: treatment, control, success, failure, and you have the margins. So, which is in this case, let's say we have 20 successes in total from treatment and control. have 10 failures in the two groups in total, and we have an equal randomization. So you have 15 patients in the treatment and 15 in the control. So it's a small sample. And you can see here, we're using the T, which is the number of successes in the treatment group, as the test statistics. You can see, as long as you know T, you know everything else in the table. And we know that from Fisher's test is that conditional on the margins, 20 successes in total, this is the distribution or the point mass of the T statistic, or sorry, test statistic T, which is a hypergeometric distribution. So it has the feasible choices from 5 to 15. That's all the probabilities associated with it. And then you can see that if we want to say we want to carry out this Fisher's exact test at level 2.5% one-sided, what will be the rejection region? If you look at the probability, the rejection region has to be 14 and 15. So it means that using Fisher's exact test, you're going to reject the null hypothesis that there's no treatment benefit if you observe 14 or 15 successes in the treatment group out of 15 total. So that is pretty high hurdle to pass, I would say. The reason is probably very obvious, is that if you look at the probabilities, the actual type 1 error rate of choosing 14 and 15 is only almost 10% of the desired level, because there's a big jump from 14 to 13. Again, because of this discreteness of the distribution. So then it's very natural to say, okay, given that we know the distribution of T, can we do some kind of optimization to fully exhaust alpha? Can we better use the type 1 error rate? This is the general idea that we want to select a subset of points of R out of the feasible points of T, such that the probability of R under the null hypothesis is as close as possible to the nominal level alpha, but still controlling alpha. So this is the basic idea to do the optimization. If you do that, you can see, interestingly, in this example, you will choose 13 and 14, because if you add the probability of those 2 points, you will have exactly 2.5%. So you will have the exact alpha level test. However, it is very odd. It's illogic that you can reject the null hypothesis when you have 13 or 14 successes in the treatment, but if you have 15, you cannot reject the null hypothesis. That doesn't make sense, right? So this gave us the motivation to add an additional requirement, which we call is no halt. So basically it means that when you try to find the rejection region, there should be no halt. So you have to include the more extreme case, or at least the most extreme value in this case. So this optimization idea is not new. So back in 1969, Pyroche had a paper. So his idea is to use optimization to find this rejection region, but the objective is trying to maximize this probability of these points under the alternative hypothesis. So similar to what we are doing for the clinical trials, we're trying to maximize our power, but controlling the type 1 error. So this is a very natural optimization and simple to do. If you do that, you will see that you will also have the situation where you will have 13 and 14 in the rejection region, but not 15. So again, probably we need to add this no-halt requirement in addition to the optimization framework. Okay, so this is something we find quite interesting, is that you could get multiplicity for free. Is that we have seen that, at least for Fisher's exact test, it is quite conservative. And the reason of its conservativeness is that the distribution is discrete. It means that even if you use some optimization technique, you cannot improve upon it. Okay, if you're still within the framework of the Fisher's exact test. However, like this 3 gears here, right? Each gear you can see is quite discrete margin. But if you have 3 gears, you can somehow complement it to the discrete distribution of them. So that's the idea of having multiple hypotheses in the framework, because you have multiple discrete distributions, then you may complement. You may fill the gaps in the distribution. So even within the multiplicity adjustment, you can make some additional rejections. So it's possible. If we go back to the example, so we know that the Fisher's exact test, you will have the rejection region 14 and 15 with the actual type of error of only 0.0026. It means that given this overall type of error rate of 2.5%, you have 0.0224 to spare on other additional hypotheses. So I want to give you a clear message that I'm not saying that you can abuse this technique to add as many hypotheses as you want. So obviously we're doing clinical trials, so the clinical consideration is something we have to consider before we enter into this scenario. Okay, so here what I'm trying to do is I'm trying to see for 2 binary endpoints, how much can we improve upon the efficiencies. So for 2 binary endpoints, the null hypothesis is that there's no treatment benefit for endpoint 1 and 2. And here we have an overall null hypothesis, that's for convenience. Here we have 2 2x2 tables for the 2 endpoints. You can see that for endpoint 1, we have total 20 successes. For endpoint 2, we have in total 22 successes. Okay, so this is something we should know before blinding. So without knowing how many in the treatment, how many in the control, we can know that, okay, so we have total 20 across the 2 treatments. So conventionally, one could use the Bonferroni test, which means that you're going to test each hypothesis at level alpha by 2. Or we can use something called optimally weighted Bonferroni test. So it's basically a weighted Bonferroni test, but the weights are kind of optimally chosen according to the distribution to mitigate the discreteness of the distribution so that we can better use loss alpha. Okay, so here you can see the general idea of obtaining the optimally weighted Bonferroni test is to choose marginal rejection regions R1 and R2 such that the sum of the type 1 error under the null hypothesis is maximized subject to some type 1 error rate control, and also we have this null requirement. Here we have 2 tables. One is the marginal distribution of endpoint 1 and one marginal distribution of endpoint 2. You can see that for endpoint 1, the Bonferroni test and the optimally weighted Bonferroni test will give you the same result. So you have to go with 14 and 15. However, for endpoint 2, you can see that the Bonferroni will also only choose the most extreme case, but if you do some optimal calculation, you can see you can also include 14 in the rejection region. And also in terms of type 1 error, you can see there's a huge jump from 15 to 14. That's how you can gain by basically assigning more weights to the second endpoint. If you look at the actual type 1 error rate, the Bonferroni is 0.037, but the optimally weighted Bonferroni is 2%. So you can improve a lot by just adding 1 point. So I think this is quite intuitive and very close to the ordinary Bonferroni, because basically we try to utilize this marginal distribution. We do some optimization so that we can mitigate the discreteness. So with that, one can very natural to extend this to the joint distribution of statistics, not only with marginal distribution, but with joint distribution. So the idea is to use the joint distribution so that we can do some optimization to find the rejection region. So the joint distribution will be similar to the permutation distribution between groups, similar to the min-p test. Okay, so this is some conditions we need to consider. So let's assume we're doing this under the global null hypothesis. And the global null hypothesis that there's no benefit on any endpoint is going to be rejected if you find your observed test statistics within this rejection region. And we have two requirements. One is the type of error control, and the other one is the no-halt condition. Basically saying if you include one point, all the points that is in the upper right corner will be rejected, so will be included. And in this optimization framework, basically we want to find the R, the rejection region, such that the probability is maximized under some assumptions. So the assumption could be the optimal exhaustion of the nominal level as much as possible that we can get close to alpha, or the optimal area of points. So we want to include as many points as possible, or we want to somehow optimize power. So this is probability under the alternative. So with these three objectives, we can do some, this is basically the binary linear integer programming. So there are some there are some available tools to use, which is the LP solver. And there are a couple of R packages, so you can do that fairly easily. But we find that because this no-halt requirement is not built in the algorithm, so it doesn't make better use of it. So we kind of modify the branch and bound algorithm behind it so that the algorithm is more efficient and more stable. Okay, if we go back to the two endpoint example, I want to show you the comparison between the two. For the joint distribution, let's assume that we have 16 successes that is both on endpoint 1 and 2. So out of 20, we have 16, 1 and 2, and 4 only successes on 1, 6 only success on 2, and failure 4. Given this, here I'm plotting the joint distribution of the test statistics. So the x-axis is T1, y-axis is T2, and this basically is a heat map. The darker the cell is, the larger the probability, or the probability mass it is with that point. So you can see the point with the largest probability is T1 being 10 and T2 being 11. Given this joint distribution, we can do the optimization, find the best rejection region, which is the red area. So the red area, so that's the upper right corner, will be the optimal rejection region to exhaust alpha. So you can see the actual type of error. I think we're doing a pretty good job. So it's almost 2.5%. The number of points is 18, and the probability under the alternative is 71%. If we do the optimization of area so that we try to include as many points as possible, so this is the plot. So you can see we did include more points. So we have 23 here, and the power is 83%. And we can also do this optimization with respect to power. So this heat map is now under the alternative hypothesis. So you can see the point mass moves towards the upper right corner. And then you can see the red cells, they're going to include the cells that has the large probabilities. So in this case, you can see the power is, when we want to maximize power, it is 86%. So this is how somewhat different result if you do different optimization. If we go back to the Bonferroni and do the comparison, let's see how can we improve for this case. We have seen two kinds of optimization under the marginal distribution or the joint distribution. Under the marginal distribution, the benchmark is the Bonferroni, so that's the first line. We have 16 points in the rejection region. The actual type 1 error rate is only 0.37%. The actual power is 42%. If we do the marginal bump cloning or marginal weighted bump cloning with some optimization, you can see we improve almost 30% in terms of power by including 6 more points. If we do this optimization jointly with respect to the joint distribution, you can see that this is the comparison. You may gain on the type 1 error with the number of points, or you may gain a little bit of power. So it's something to discuss with the team with the best solution you want. But hopefully we can see that using some optimization definitely is much better than applying Fisher's exacts in combination with bump cloning, which is kind of a combination of 2 conservative tests. So some conclusions. I think for clinical trials with small sample sizes, exact test is usually more suitable because the approximation is not working so well. But we see that multiplicity, testing multiple hypotheses may give you some benefit in this case. And especially if you're dealing with multiple discrete distribution, it's beneficial to do some optimization. And finally, some extension is that you can see that I'm showing the result for the overall null hypothesis, but you can extend this to the closed procedure so that you can control the family-wise error rate. And you can, since we're dealing with the rejection region, so we're no longer dealing with p-value, we're dealing with each point. So it means that you can do some tailoring so that the procedure is constant. So there is some shortcut procedure, or you can ensure some alpha consistency, and also for trial planning you can even consider additional power, which is involving permutation of all the combinations of the 2x2 table. So I think that's it. Some references, and thank you very much.
Thanks again. So we do have 1 minute left. Oh, maybe 0 minutes left before discussion. Just a quick question. Anyone has a quick question?
But that is something I didn't focus on, is this exchangeability condition. So currently the calculation is under the point null hypothesis, where basically we're saying there's no treatment effect, but the treatment effect for the treatment is equal to the control. So we're not dealing with the situation where the treatment is actually worse than control, which I think will be out of this exchangeability condition. But in terms of real examples,